Hi there, and welcome to this lesson. In this lesson, we're learning differential calculus, okay? And under differential calculus, we would be learning to differentiate from the first principle. Interesting. So, at this point, I'd remind you to set the video to play in 1080p HD. Very important that you do so. And as the lesson progresses, if you have any issues at all, please feel free to get in touch, okay? You can do so via the course dashboard. Okay, let's jump right into the lesson. So, differential calculus, differentiation from the first principle. Now, what exactly is calculus? Okay, now calculus is a mathematical study of continuous change. Okay, and that would get clearer as the lesson progresses. So calculus is a mathematical study of continuous change, and differential calculus is a subfield of calculus. Okay, the other subfield being integral calculus, but differential calculus is a subfield of calculus that covers the study of the rates at which quantities change. Okay, and if when you say the rates at which quantities change, the first thing that should come to mind should be gradients, okay, because gradients is pretty much expresses the rate at which quantities change. For example, if you have a graph like this, you'd have s on the y-axis representing distance, and t on the horizontal axis representing time. I never understood why we represent distance with s, but basically that's the norm. So we have s as distance as and t as time. Now, consider a body moving following the straight line graph. Okay, so we have a body whose and the distance covered by this body is increasing with time. Okay, so we have a straight line graph here, and basically at this point A, at an instance as the body was moving, it had covered 30 meters in 10 seconds. Okay, so we have 30 meters in 10 seconds at an instance A. Okay, and then we have another instance B. Okay, and at B the body had covered a distance of 90 meters and it had done that under 30 seconds. Now, if you want to find the rate at which the distance is increasing with the time, okay, so the rate at which the two quantities change, it simply go ahead and find the gradient of this line. Okay, and if you solve for the gradient of this line, you would have 3. And what exactly is 3? 3 is the speed. Okay, is the speed of the moving body, and you can say the function of this moving body is s equals 3t. Okay, so that is pretty much standard. Okay, when you're studying the rate at which quantities change, okay, you have distance and time in this case. But then very often, where exactly does differential calculus come in? Now, very often bodies don't move as simply as this. Okay, so we have a body moving with uniform speed in this case, and the graph of the distance against time is a very simple, beautiful looking straight line graph. But very often bodies move in more complex forms, okay, and that is where differential calculus comes in. Okay, now consider a body moving following a function y equals x squared. Okay, so we have a function y equals x squared, and this body is moving following this function y equals x squared. And then if you plot the graph of y equals x squared, what you would end up with is a curve. You wouldn't end up with a straight line, you would end up with a curve. Now, if you ask to find the rate of change of y with reference to x, how would you go about doing so? Now, you can't do the simple process of finding the gradient following using 2 points on the curve. It would not work. Reason being, there's something quite complex about curves, is that the gradient at different points is actually different. It's not a fixed gradient like we had for this line, where for the line we had before, the gradient is fixed. The gradient is always 3. Okay, but for this curve, the gradient is different at every point. Now, if you consider this point A and you're looking to find the gradient of the curve at point A, what you'd have is you'd have the gradient of the gradient of the curve at point A is the gradient of the tangents to the curve at point A. Now, if you had another point, now the tangent of the curve at point A is a line that cuts through the curve at just that point A. It doesn't cut through any other point. Now, if you had another point B, okay, and obviously the line does not cut through, it does not cut through point B. If you had another point B, okay, the gradient at point B would be completely different from the gradient at point A. You'd actually have another tangent to the curve at point B, and the gradient at point B would be the gradient of the tangent to the curve at point B. Okay, so how do we go about studying this? How can we find the gradient of this curve? And that is where differential calculus comes in. And now what we're going to do is we're going to introduce a change in x. Okay, a change in x. Okay, and remember, calculus is a subfield of differential calculus is a subfield of calculus that studies the rates at which quantities change. So we're pretty much trying to find the gradient of this curve. Okay, so we introduce a change in x and we'll call this delta x. Okay, and you introduce a change in y and we call this delta y, and what we're simply looking for is the gradient. So what we want to find in the end is a change in y divided by a change in x, i.e. delta y divided by delta x. Now how do we go about doing this? Now our function is y equals x squared. Okay, and then if I introduce the change in x, okay, so that I bring in delta x, I add delta x to x, what would the result of that would be y would be a change in y. Okay, the resulting change in y, delta y. So if you add delta x to x and square it, your result would be y plus delta y, because the function you have here is y equals x squared. Okay, so x plus delta x all squared would be y plus delta y, an increase in x resulting from bringing about a complement, bringing about an increase in y as well. Okay, so now once we have that, we can simply go ahead and expand that. So we have x plus delta x all squared. It will give me x squared plus 2x delta x plus delta x all squared. Okay, so once I have that, I can go ahead and substitute x squared for y. Remember that y equals x squared, so I can say instead of y plus delta y, I can say x squared plus delta y. Okay, and then I'll move x squared over to the right, and what I have is I have delta y equals x squared plus 2x delta x plus delta x all squared minus x squared. Remember what we're trying to arrive at here. We're trying to get delta y over delta x, i.e. the gradient of the curve. Now, I can then say, because we have x squared and minus x squared, I can cross those out. I can then say delta y equals 2x delta x plus delta x all squared. And then I'd factorize what I have on the right with delta x, and I have that delta y equals delta x multiplying 2x plus delta x. And then what I have is I can divide both sides by delta x, and I have that delta y equals 2x plus delta x. So we have delta y over delta x, the ratio of a change in y and a change in x, i.e. the gradient to the curve. But there's something important we have to do at this point. Now remember, the gradient is different at every point, okay, and we're actually looking to find the gradient at a particular point. Okay, and if you're finding the gradient at a particular point, it means there really isn't a change in x. It's a very interesting concept, okay, because basically we're trying to find, for example, let's take point A. We're trying to find the gradient at point A. Now the gradient at point A would be, the gradient at point A would not there isn't a second point, okay, so we just have one point, but and then there isn't a second point, so we really don't have a change in x at the one point A. Okay, But then we obviously can't solve gradients with just one point. So what we do is we actually find a second point that is actually really close to A. Okay, it's so close to A that the difference between that point, the difference between point A and that other point, the change in x, is pretty much negligible. Okay, it's pretty much zero. Okay, so what we do is we find the limit, we say dy dx, and that is how we represent derivatives. When you find, using differential calculus, when you find the derivative of a function, you say dy dx. So dy dx is the limit of 2x plus delta x as delta x tends to 0. Okay, because I said you introduce a point that is so close to the point A that the difference in x, delta x, is pretty much 0. Okay, so find the limit of the function 2x plus delta x as delta x tends to 0, and what we have in the end, delta x pretty much becomes 0, and we have that dy dx equals 2x. And that's how you differentiate from the first principle. Okay, so you have a function y equals x squared, the y dx is 2x, and what this simply means is that the gradient at the point A would be 2 times the x value at point A. Okay, and then the gradient at point B would be 2 times the x value at point B for the function y equals x squared. Now, I'd like you to try finding the derivative of the function y equals x cubed. I think you can give it a go. Okay, it's not too difficult once you follow the standard principles. Basically, you'd have that y equals x cubed, you'd have that y plus delta y equals x plus delta x all cubed, and then you expand, you subtract, you factorize, and from there you'd get the ratio delta y over delta x, and then you find the limit as delta x tends to 0, and you should arrive at an answer 3x squared. So go ahead, give it a go. Bye for now.